Alright, so today we're going to be talking about Chapter 4, Section 5, Integration by Substitution, which we call U-Sub. So right now our understanding of the integral is pretty limited. Right now all we know is that the integral is big F of x plus c, where big F of x is the antiderivative of the integrand, or the antiderivative of little f of x. So let's take a look at f of x equals the quantity x squared plus 9 to the 6th power. If we wanted to derive this, everybody looks at it and goes, okay, that's a chain rule. So f prime of x is equal to d out of in times d in, or 12x x squared plus 9 to the 5th power. So what that means is if I was trying to integrate 6 times x squared plus 9 to the 5th power times 2x, it would be the antiderivative plus c. Well, that would mean that this integral should be equal to x squared plus 9 to the 6th power plus c, because when I took the derivative of this, I got this thing right here. And U-substitution is the means with which we can get that. To use U-substitution, you have to set u equal to what the in was in the chain rule. So for this example, u would be equal to x squared plus 9. That's what the in was. The derivative of u would be equal to 2x. So I can substitute back into that integrand and rewrite that integrand as the integral of 6 times x squared plus 9 to the 5th, but x squared plus 9 is u to the 5th, and 2x dx is equal to du. Now I've got it. I used U-substitution, and I have it written in a form that I can reverse power rule. Right? If I integrate 6 u to the 5th du, I would get u to the 6th plus c, resubstitute in, and I would get x squared plus 9 to the 6th power, because I substituted in, because that is equal to u, plus c. So basically we're learning the unchain rule. U-substitution is a method of integration where I substitute in u and du and I get a form that I can reverse power rule. Once I get it into a form I can reverse power rule, I just apply that reverse power rule. So the integral of u to the z du would just be, there's our reverse power rule, add 1 to the exponent, divide the old coefficient, which in this case is 1, by the new power. So let's try a few U-sub or unchain rules. So remember, this came from a chain rule. I want to set u equal to whatever the in was. Well, if this was the result of a chain rule, the in would have been 6x minus 3. If that's u, then du is just equal to 6 dx. Substituting that back in, I can rewrite my integrand as u cubed, and the 6 and the dx become my du. The integral of u cubed du is just 1/4 u to the 4th plus c. So this is now my integral. Substitute back in my u, and I end up with 1/4 6x minus 3 to the 4th power plus c. As with any integral, I can check it by deriving. If that's y, then y prime is equal to, I would do d out, which is of n times dn, which is 6. So I end up right back with the integrand I started at. I'll give you about 90 seconds to use U-substitution to integrate this problem. Alright, so I want to set u equal to what the in was in my chain rule. That would be 2x cubed plus 9. Then du is equal to 6x squared dx. So I can rewrite this as u to the 4th du, the integral of which is equal to 1/5 u to the 5th plus c, or 1/5 substitute back in 2x cubed plus 9 to the 5th plus c. So you're probably thinking, it can't be this easy the whole time. All right, sometimes you need a constant to make it work. So for this problem, again, I set u equal to what the in was. That would have been 2x squared minus 3. And then du is equal to 4x dx. Well, that causes a little bit of a problem because I have the dx and I have the x, but I don't have the 4. All right, so I'm missing part of my du. I can multiply the inside by 4 to get that 4x dx as long as I multiply the outside by 1/4. Because if I multiply the inside by 4 and the outside by 1/4, I essentially multiplied that integrand by 1. If once I do that, I can rewrite this integral as 1/4 the integral u to the 7th du, which would be equal to 1/4 times 1/8 u to the 8th plus c, or 1/32 times 2x squared minus 3 to the 8th power plus c. There's no need to distribute that 1/4 to the c because c times 1/4 is just going to be another constant. So it sort of is like a black hole. It just sort of sucks all the constants that are multiplied by it up. I'll give you 60 seconds to try this one. Alright, so u is the in, that would be x cubed plus 4. Du is equal to 3x squared dx. So I need a 3 as my integrand, so a 1/3 out in front, so they cancel. This is now 1/3 the integral of u cubed du, or 1/3 times 1/4 u plus c, or 1/4 u to the fourth plus c, or 1/12 times x cubed plus 4 to the fourth power plus c. Just like the chain rule can get more complicated, so can U-substitution. So here this problem's a little bit different because I got a trinomial as my in. So u is equal to x squared plus 4x plus 9. That's my in. That was what the in was. So then du is equal to 2x plus 4 dx. I almost have my du. I'm just missing, I need a 2 times that x and a 2 times that 4, which is fortunate. So if I multiply the integrand by 2 and the outside of the integral times 1/2, I have 1/2 u to the 7th du, which is 1/2 times 1/8 u to the 8th plus c, or 1/16 x squared plus 4x plus 9 to the 8th plus c. U-sub works with fractional exponents as well. All right. Clearly that x squared plus 3 is the u, because that was the in from my chain rule. My du would be equal to 2x dx. So I need a 2 in my integrand and a 1/2 out in front to cancel it. So this would be 1/2 times the integral of u to the 1/2 du, or 1/2 times 2/3 u to the 3/2 plus c, or 1/3 times x squared plus 3 to the 3/2 plus c. In your remaining time today, complete the following problems. Anything you don't finish should be finished for homework, and the answers will be on Edmodo. If you have any questions not answered by the answer key, feel free to message me on Edmodo. Have a good day.